Hello everyone, myself P. Jithendar, Assistant Professor in Electrical and Electronics Engineering, MLR Institute of Technology. In today's video session, I am going to discuss about the EMF equation of single phase transformer. So here, before that, what is the principle of this transformer? What is the statement of the transformer? So it is a static device. The electrical power is transferred from one circuit to another circuit without changing its frequency. That is according to Faraday's law of electromagnetic induction, right? So by using the Faraday's law, I need to derive the EMF equation of the single phase transformer. Okay, so here we are having the derivation part of the single phase transformer. So here, let us consider phi is flux, N1 is primary number of turns. So this is primary number of turns. N2 is secondary number of turns, N2, and we are having the primary and secondary voltage. So V1, so primary voltage, V2 secondary voltage, right? So V1 is the primary voltage and V2 is secondary voltage, and E1, E2 also is there. So E1 is primary induced EMF. Primary induced EMF, that is E1, and E2 is secondary induced EMF, right? So here phi is flux, N1 is primary number of turns, N2 is secondary number of turns, V1 primary voltage, V2 is secondary voltage, and E1 is primary induced EMF and E2 is secondary induced EMF, right? Now according to Faraday's law, the EMF equation is equal to N into d phi divided by dt. So here, according to Faraday's law, equal to N into d phi divided by dt. Here I am taking the one conductor here, that is N is equal to 1. Then E equal to, will get d phi divided by dt. Okay, so d phi is change in flux and dt is change in time, right? So here, so we are giving the AC supply to the single phase transformer. So if it is a AC supply, means we will get the sinusoidal waveform. So here is the sinusoidal waveform will get. This is flux with respect to time. So flux with respect to time. So here we are having the maximum flux, that is phi. Now the intervals are, this is 0, pi, and this is 2 pi. Now for this sine wave, the total time period t equal to 1 by f. For the full cycle, t equal to 1 by f. For the half cycle, the total time period t equal to 1 by 2f. Now at maximum flux, we are having the t equal to, time period t equal to 1 by 4f, right? And here the flux is changed from 0 to phi, right? So here change in flux is there, d phi is change in flux, that is equal to phi m minus 0. So that is equal to phi m minus 0 divided by dt, means change in time. So the change in time is t equal to 1 by 4f. So dt is 1 divided by 4f, right? So now E equal to, will get 4F phi m. This EMF equation for the one conductor. Here F is frequency, phi m is the maximum flux, right? So if it is, we are having the form factor for all the AC quantities. We are having the form factor. So form factor is defined as it is the ratio of the RMS value and average value, that is equal to 1.11. Form factor is defined as it is the ratio of the RMS value and average value. So form factor for the all the AC quantities are 1.11. Now multiply with E. So E equal to 4F phi m into 1.11. So we'll get E equal to 4.44 F phi m. Suppose if you need to find out the primary induced EMF, the EMF equation is E1 equal to 4.44 F phi m N1. This is the primary induced EMF. If it is a secondary induced EMF, E2 is equal to 4.44 F phi m N2. So this is the primary induced EMF, E1 equal to 4.44 F phi m N1, and here this is the secondary induced EMF, E2 equal to 4.44 F phi m N2. So E1 value and E2 value. In generally, the EMF equation is written as equal to 4.44 F phi m N, where phi m is equal to B max A. Maximum flux is equal to maximum flux density into area of the core. So phi m is equal to BMA. Okay, this is the derivation part of the EMF equation of single phase transformer, right? So for this EMF equation of the single phase transformer, we'll discuss the problems here. So we are having the first problem. The voltage ratio of a single phase 50 Hz transformer is 5000 by 500 volt at no load condition. So in that case, we need to calculate the number of turns in each winding. You have to calculate the number of turns in each winding. If the maximum value of the flux in the core is 7.82 milliweber. So here, first we have to write the given data first. So the voltage ratio of the single phase transformer, that is E1 or V1, is equal to 5000 volts. So this is primary induced EMF or primary voltage, and secondary induced EMF or secondary voltage is 500 volts, and frequency also is there, F equal to 50 Hz at no load. So calculate the number of turns in each winding, means we need to calculate the N1 value and N2 value, and the maximum value of flux. So the maximum flux phi m is equal to 7.82 milliweber, that is equal to 7.82 into 10 to the power of minus 3 Weber, right? So here is the given data. So E1 or V1 is equal to 5000 volts, E2 or V2 equal to 500 volts, and frequency F equal to 50 Hz. Then we have to find out the primary and secondary number of turns, and the maximum flux also is there, that is 7.82 milliweber, right? So here already we know about the transformation ratio, that is E2 by E1 is equal to N2 by N1, that is equal to V2 by V1, that is equal to I1 by I2. So here V2 by V1 equal to E2 by E1 equal to N2 by N1 equal to I1 by I2 is nothing but it is a transformation ratio. In terms of the voltage, it is V2 by V1. In terms of induced EMF, E2 by E1. In terms of number of turns, N2 by N1. In terms of currents, I1 divided by I2. That is equal to some constant K. Right? So now we have to find out the primary and secondary number of turns. So here I am using the primary induced EMF equation, that is E1 equal to 4.44 F phi m N1. Now by using this equation, we need to calculate the N1 value, that is primary number of turns. So N1 is equal to E1 by 4.44 F phi m, that is equal to E1 5000 by 4.44 into frequency 50 into maximum flux 7.82 into 10 to the power of minus 3. Now by solving this equation we'll get 2880 turns for the primary number of turns. Now for the secondary number of turns, we have to use the transformation ratio, that is E2 by E1 is equal to N2 by N1. So already we know the N1 value 2880. Now we need to calculate the secondary number of turns, that is N2 equal to N1 into E2 by E1. That equal to, what is N1? 2880 into E2 secondary induced EMF 500 divided by 5000. Now by solving this equation, we'll get secondary number of turns, that is 288 turns. Here is the primary turns 2880 and this is the secondary number of turns. Here is the calculation part of the primary and secondary turns. Okay, and we will go to next problem. So here a transformer with 1000 primary turns and 400 secondary turns is supplied from a is supplied from a 220 volt AC supply. So we need to calculate the secondary voltage and volts per turn. So in this problem, we need to calculate the secondary voltage. We need to calculate the secondary voltage V2 and also we need to calculate volts per turn. Right? So here first we have to write the given data here. So a transformer with 1000 primary turns means N1 equal to 1000 primary turns and N2 equal to 400 secondary turns is supplied from a 220 volt AC supply. That is primary voltage V1 equal to 220 volts. Then we need to calculate the secondary voltage, that is V2 and volts per turn. We need to find out, right? So here, so the secondary voltage. So already we know the transformation ratio V2 by V1 in terms of voltage. V2 by V1 is equal to, in terms of number of turns, N2 by N1, right? Now by using this equation, we have to calculate the secondary voltage, that is V2, where V2 equal to N2 by N1 into V1. That equal to, what is N2 value here? N2 is 400, N1 is 1000 into V1 220. Now by solving this equation we'll get 88 ohms, right? So here is the secondary voltage, and we have to find out the volts per turn. That means, so I'm taking the primary side, so V1 per turn N1. So V1 by N1 equal to, so V1 is 220 volts divided by N1. So what is N1? N1 value 1000. So V1 by N1, that is equal to, we'll get 0.22 is the volts per turn. Okay, so secondary voltage V2 is equal to 88 volts, and volts per turn, that is V1 by N1 is equal to 220 by 1000, that equal to 0.22. Okay, here is the solution for the given problem. And next we are having the 80 kVA. So here the power rating of transformer is given. 80 kVA 3200 by 400 volts. Single phase 50 Hz transformer has 111 turns on the secondary winding. So calculate the number of turns on primary winding, and second bit is secondary full load current, and third one is cross sectional area of the core if the maximum flux density is 1.2 Tesla. Okay, so here a 80 kVA is there. So here a 80 kVA is nothing but, that is power rating of transformer. So P equal to 80 kilovolt amperes, that is equal to 80 into 10 power 3. 1K is 1000, that is 10 power 3 volt amperes. Okay, and 3200 by 400 means primary E1 or V1 equal to 3200 volts, and secondary E2 or V2, that is equal to 400 volts. Single phase 50 Hz frequency F equal to 50 Hz. Transformer has a 111 turns on the secondary winding, means N2 equal to 111 turns on the secondary winding. Then we need to calculate the first bit, number of turns on the primary winding. So already we know the equation, E2 by E1 is equal to N2 divided by N1, right? So here primary number of turns on the primary winding means N1 equal to N2 into E1 by E2, that is equal to, what is N2 here? 111 into E1 3200 by 400. Now by calculating this, we'll get primary number of turns, that is 888 turns. Here is the first bit. N1 is equal to, by using the transformation ratio in terms of the EMF, E2 by E1 is equal to N2 divided by N1. By using that equation, we'll get N1 is equal to N2 into E1 by E2. If you can substitute all the values in this equation, we'll get primary number of turns, that is 888 turns. And second one, secondary full load current. So we need to calculate the secondary full load current. So here, so we are having the power rating here, power rating of transformer P equal to 80 into 10 power 3, 80 into 10 power 3 volt amperes. So we need to calculate the secondary full load current. So secondary side we need to calculate. That means, so generally power equation P equal to V into I. So secondary side V2 into I2. So V2 into I2 equal to 80 into 10 power 3. Then secondary current I2 equal to 80 into 1000 divided by V2, or I2 equal to 80 into 1000 divided by V2 value. Secondary voltage V2 is 400. Now by solving this equation we will get 200 amperes is the secondary current. Second bit. And third one, cross-sectional area of the core if the maximum flux density is 1.2 Tesla. So cross-sectional area means we need to calculate the A value. We need to find out A. So in that I am taking the primary EMF induced EMF equation E1 equal to 4.44 F phi m N1, where phi m equal to, since we know the equation, B max A. So substitute here E1 equal to 4.44 F into phi m B max A into N1. So in this equation we need to calculate the area of the cross section, that is A equal to E1 by 4.44 F into B max into N1, that equal to, so E1, what is E1? 3200 divided by 4.44 into frequency 50 into maximum flux density B max. So B max is 1.2 Tesla. So B max is 1.2 into primary number of turns N1 888. Now by solving this entire equation we will get 0.0135 meter square. Here is the area of the core, right? So here by using that given problem we will get primary number of turns and secondary full load current and area of the core, right? Here is the some problems on the EMF equation of single phase transformer. Okay, so thank you one and all.